So let's take a look, okay, of these two interesting properties. So here, according to part A, we are going to show something called the Euler's theorem here. So Euler has so many theorems. And then here, this is about the theorem that is about the totient function, Euler function. So Euler's theorem is a to the power phi of m is equal to 1 modulo m if the GCD of a and m is equal to 1. Okay, so this is it, Euler's theorem. If you look at it, this is a generalization of the Fermat's-Little theorem. Because when you plug in P here, so it says that a to the power phi p is equal to 1 modulo p whenever a and p they are coprime. And then it turns out that phi p is equal to p minus 1. So if you remember Euler's theorem, then you can ignore Fermat's-Little theorem, because this is the general version. If you know this, you know that. Is that okay? And the proof is very similar. Very similar. So let's prove this. So let's consider the numbers from the numbers. So let's take a look of all the numbers less than m. So you have 1, 2, 3, and then m minus 1. So let's consider these numbers. Okay, and then exactly, so by the definition of this phi, exactly phi m of them is coprime with m. Okay. So let's so for easier illustration, let's take a look of a particular m. Let's say m is equal to 10. Is that okay? So when m is equal to 10, then phi of m is equal to 4. Is that okay? And then exactly how many of them? So exactly, so we are looking at the numbers 1, 3, 7, and 9. Is that okay? Is that okay? Okay. Now, let's multiply a to every of them. This number a, so you use this a, okay, make sure. Let's multiply a to each of them. So okay, so first of all we have phi m numbers here. We find m numbers all coprime with m, and then we multiply a with them. So multiply a with them, multiply a with them, multiply a with them, and multiply a with them. So we multiply a with them, all of them. Then what will happen? Then So we will have two things. The first thing is all numbers after the multiplication with A, they are still coprime with M. Does that make sense? Or originally, there is no common factor. And then you multiply A to each of them. Okay? A doesn't have any common factor with M from the beginning in the theorem. So you multiply an A, so you still do not have any common factor. Okay? And then the second one is all numbers are not congruent to each other. So all numbers are not congruent to each other. Yeah, how can we prove? Okay, so let's say you have this number I here, and let's say this number J here. So there are two numbers. Okay. Now if A times I is equal to A times J modulo M, then what we can do? Okay, this is about M, and then A has greatest common divisor with M equal to 1. So there exists the inverse of A here in this modular arithmetic. Yeah, because GCD of A and M is equal to 1, this implies there exists some number A inverse such that A inverse times A is equal to 1 modulo M. Is that okay? Definition of GCD, right? So in that case, we can multiply this one with A inverse, multiply this one with A inverse, and it still holds. That this implies that I has to be equal to J. Is that okay? So here it means that there are two things. First of all, after multiplying with A, everything is still coprime. And then they are still all different. Then what does that mean? So what does that mean? It means that before we do the multiplication, we have a set of numbers. After the multiplication, we still have the same set of numbers. It is just a permutation only. Is that okay? Before the multiplication, we gather all the numbers coprime with M. After that, we still have a group of numbers. All of them are coprime, and they are all distinct. So it must be the same as the original set. Okay? So in that case, what? In that case, if we multiply everything together, so we have A of the first number. So let me give it a name. So let's call this I1. Let's call it I2. Let's call the last number I of phi M. Is that okay? So we have A times I of 1, this number, times A of I times A times this number. We multiply all of them together. So this is what we have. It will be the same as if we don't have this A at the beginning. So all the things are talked in the modulo M arithmetic case. Is that okay? Is that okay? Then each of these numbers are coprime with M, so the inverse of them with respect to this modulo M exists. So you can actually do division. So you can divide I1 by multiplying the inverse of I1. You can divide I2 by multiplying the inverse of I2, and so on and so forth. So this implies, after doing the division, you will have A to the power phi M is equal to 1 modulo M. Okay, so this is what we get. Extremely similar to the proof of Fermat's-Little theorem, or the same idea. Is that okay? Good. So we have done this one. And then the next one, let's show that it has this multiplicative function property. So not just phi, there are other types of function that has multiplicative property. So okay. Okay, so but let's look at phi first. Okay. In fact, we show an even stronger theorem rather than showing that it has multiplicative property. We have a closed form for what is phi n. So we have another theorem. Phi of n is equal to n times the product of prime p that divides n 1 minus 1 over p. Is that okay? So yeah, so phi 1 is special. Phi 1 is equal to 1. Or for phi 1, you have n is equal to 1, and this part you don't have any prime dividing n. So automatically this part you set it to 1. Okay? So phi 1 is equal to 1. It is okay. But we want to show that this is true in general. Okay, and then the proof is by induction. Wow, very interesting. By induction. But this is not by induction on n. So it's not like you have a way to prove that n is equal to 1, n is equal to 2, n is equal to 3, then we get n is equal to 4. It's not like that. It's by induction on the number of prime factors of n. Is that okay? Okay, the number of prime factors. For instance, 10 has 2 prime factors. 10 can be divided by 2 or 5. Okay, 9. 9 has only 1 prime factor. There is only 1 prime, 3, in the whole universe that can divide 9. Okay, so we are looking at the number of prime factors. So, okay, so I'll use the board over there. So let's give it a name. The number of prime factors, let's give it a name. Let's call it R. Okay, let's say R denotes the number of prime factors. Is that okay? Okay, so we want to show that basis case and also the inductive case. So the basis case is when R is equal to 1. Is that okay? And then later, when we want to show the inductive case, we want to show that if the theorem works for R, it also works for R plus 1. Is that okay? Is that okay? So this is what we are going to do. So if we have the basis case and the inductive case both proven, then we are done. Okay? Okay, now, so R is equal to 1. This implies what? This implies n has only 1 prime factor, right? So then n is equal to p to the power k for some prime p and some integer k greater than 1, greater than or equal to 1. Is that okay? Okay, now we want to talk. So here we want to look at what? So we want to look at phi of n, right? And phi of n is equal to, because n is equal to p to the power k, it is equal to phi p to the power k, right? And then remember, what is phi? Phi is asking how many numbers from 1 to p to the power k co-prime with p to the power k. Okay. So what can be a number? So we want to ask we want to ask those that are co-prime. So we can think of this in the reverse way. How about the number of numbers that are not co-prime? Not co-prime with p to the power k. What are the numbers that are not co-prime with p to the power k? So it will have some common factor, right? If a number is not co-prime to p to the power k, then it must be divisible by p. Is that okay? If it's not co-prime, so we have p to the power k here. We have p to the power k here, and then let's say some number x, okay, not co-prime. So the GCD is greater than 1. Then if it is greater than 1, then it's greater than or equal to p, right? And actually, p to the power k has what kind of factors? 1, p, p squared, p cubed, p4, up to pk, right? So if x is divisible by p, then the GCD is greater than or equal to p. On the other hand, if the GCD is greater than or equal to p, then x is going to be divisible by p, right? So this is actually an if and only if condition. So the numbers that are not co-prime will be those numbers divisible by p. Okay, how many numbers are there divisible by p? So we are looking at the numbers from 1, 2, 3, 4 up to p to the power k, right? How many of them are divisible by p? How many? So you go to p, you have the first number, and then the next number 2p, and then 3p, and then 4p, up to p to the power k minus 1 times p. So here, so exactly p to the power k minus 1 numbers are divisible by p. Is that okay? Good. So we know what is this one. So phi p to the power k is equal to the total number p to the power k minus the number that is divisible by p. Is that okay? So this is equal to p to the power k times 1 minus 1 over p. And then done. Yeah, this is the form that we hope. If you are okay with this, could you please raise your hand? Okay, good, excellent. Now, how about the case where n has more than one prime factor? So here, so we can assume that n is equal to some n prime times some number p to the power k with what? P do not divide n prime, and p is a prime, and so this n, you can use this logic n, and n prime has R prime factors. Is that okay? So when we are looking at the number that has a lot of prime factors, then what do? We take out one of the prime factor, let's say p. We take out as many as possible. So we get p to the power k, such that the remainder is not divisible by p. Okay? Okay, so let's use an example. Okay. So let's use an example. Suppose that n is equal to 36. Is that okay? Is that okay? So 36, you can think of this as equal to 9 times 2 to the power 2. So we take out these numbers. Okay? Now the proof, let's use this as an example. The proof is following this way. So what we are going to do, we are going to write down the numbers. Let's write down the numbers in this form. Such that there are n prime numbers here. So this is n prime. And this is p to the power k. Is that okay? Such that there are n prime numbers here, and then there are p to the power k numbers here. Is that okay? Okay. Let's write down the numbers one by one. So we have what numbers? So we have 1, 2, 3, 4, 5, 6, 5, 6, 7, 8, 9, and then 10, 11, 12, 13, 14, 15, 16, 17, and 18 here. Is that okay? And then 19, 20, 21, 22, 23, 24, 25, 26, 27. Okay? 28, 29, 30, 31, 32, 32, 33, 34, 35, and 36. Is that okay? Okay, now, so we have written down all the numbers here. Okay, and then what we are going to look at. Okay, so let's look at the numbers here. Let's, first of all, circle all the numbers that is co-prime with n prime. Just co-prime with n prime. We need this one. So what is co-prime with n prime? So 9 here. So the first, let's take the first row. The first row is 1 to 9. So what are co-prime with 9? So n prime is equal to 9 here. Okay, so 1 is co-prime, 2 is co-prime, 4 is co-prime, 5 is co-prime, right? 7 is co-prime, 8 is co-prime. That's it, okay? Now how about the second row? Which numbers will be co-prime with n prime? Well, the second row is equal to the first row plus n prime, right? So it is going to be co-prime with n prime if and only if the number in the first row is co-prime. Okay, so 10 is co-prime, 11 is co-prime, 13 is co-prime, 14 is co-prime, 16, 17. That's it. And the third row, so these numbers are co-prime. And then these numbers are co-prime. Okay, so what do we have? So we have a fact. So we have this observation. So now, so we have exactly what? Exactly p to the power k times phi to the power n prime numbers are co-prime with n prime. Is that okay? Exactly these numbers. But then we are not focusing on this. We want to find out the numbers that are co-prime with n. So what we need to do, among all these numbers, we need to find out what are the numbers that is co-prime with 2 to the power 2. So we need to cross out. So that's too many. Too many. We need to cross out. So what are the numbers that is co-prime? So if you look at this, we will say that every p number here, so p is 2 here, every p number, there is 1 divisible by p. Is that okay? So because, let's say this number is called I, okay, so we are looking at what? I plus n prime, I plus 2n prime, and so on and so forth, up to I plus a lot of n prime. But let's look at the first p of them. So I plus p minus 1 n prime. Okay, is that okay? So among these p numbers, one of them will be divisible by p. And then among the next p numbers, one of them will be divisible by p, and so on and so forth. So among all these p to the power k numbers in each column, 1 over p of them is divisible by p. Every one number in p numbers is divisible. Every one number is, so here, so let's say in this example p is equal to 2, so this is divisible by 2, I don't want this. This is divisible by 2, I don't want this. Is that okay? And then for this column, this is divisible by 2, I don't want this. This is divisible by 2, I don't want this. Is that okay? And then this is divisible by 2, I don't want this. Divisible by 2, I don't want this. Divisible by 2, but I don't want this. Divisible by 2, I don't want this. Divisible by 2, divisible by 2, divisible by 2, divisible by 2. Is that okay? Okay. So we have this is just talking about coprime with n prime. And then 1 over p of them are not coprime with p. Is that okay? So in that case, then we will have, if you go back to this one, we will have, let me try this. We will have, so what is phi of n? Phi of n is going to be, we look at the final result. Phi of n is equal to p to the power k phi of n prime times. So among all these numbers that are coprime with n prime, a fraction of 1 over p is not coprime with p. So we need to deduct this. Is that okay? Good. This is a new prime that we have not considered. This has only R factors. So if you like, then we can write it down as this is equal to p to the power k times 1 minus 1 over p. We take it out. Because this is what? This is only having R factors rather than R plus 1 factor. Induction hypothesis says that, okay, this is going to be written as n prime times the product of, well, I use a different notation, q here, that divides n prime, 1 minus 1 over q. Is that okay? Now, pk times n prime, this gives us n. Is that okay? 1 minus 1 over p times this one gives us this. We are going to take out all the primes that divides n, 1 minus 1 over q. Is that okay? So we prove the theorem. Is that okay? So the most important thing here is that we visualize that by arranging the numbers in this rectangle form, then we can help us, so it can help us count what are the numbers that is coprime with n and what are not. Then in that case, we get the result. Okay. Oh, that seems to be too much for you for the first lecture. So let's take a break. And then let's take a 15-minute break. Let's come back at 3:30, and then we will talk about the RSA scheme. Okay, thanks.